Hi, good morning. So as Jamie said, I'm going to be talking to you a bit about my laboratory experiments to understand space weathering's effects in the mid-infrared. So this one? This one? Okay. Maybe? Okay. So I'm sure you've seen Sarah Noble's lovely cartoon about space weathering, and it's just the summation of all of these micromedium bombardments and solar radiation and solar wind on the regolith surface and its effects on the regolith. And so why we really care is how it affects the regolith itself. And so I've just shown you a couple of the images from Carly Peters' 2000 paper of the nanophase iron rims that form due to space weathering. And so overall, we just get both physical and chemical changes to the regolith, and this manifests optically as well. And a lot of visible near-infrared work has been done characterizing this, but less so in the mid-infrared. And Lucy et al. Just had a paper out actually remarking on the fact that we see this effect in VNIR lunar radiometer data, and it's affecting the CF position, which is what VNIR looks for to understand silicate mineralogy on the moon. So I've just shown one of his figures here where he uses the optical maturity index map to try to correct for the space weathering effects. So again, what I want to do is look in the lab and see that if we can really characterize this well on Earth. So when we're looking in the mid-infrared, we also have to take into account the lunar environment, the lunar thermal environment. So I tried to show you in this little diagram. Is there a pointer? Oh, gotcha. Okay. Try to show you with this little diagram here how this works. We have, the sun coming in, warming the regolith, but due to the fact that it's an airless body, we don't have interstitial gases to help move that heat around. It makes it very inefficient. So at the very surface where it's exposed to the cold vacuum of space, it's much colder. We end up with a thermal gradient. And when our instruments are looking at this, what happens is we get some warmer temperatures mixed with colder temperatures, and this affects our spectra. And just to show you this plot from Henderson and Joukowsky in 1997, you can compare the gradients on the moon, which is very extreme, to Earth, which is practically non-existent at the hundreds of microns scale depth. And then Mars also has a little bit, but not too much. Okay, so in the mid-infrared, this is a typical mid-infrared spectra that I'm working with, and I just want to point out some of the features that I'm looking at when I do this analysis. So this is a Forsterite spectrum, and we have wave number on the X, emissivity on the Y. One of the main features that I'm looking at due to working with the VNIR instrument is the CF, which is this peak here. And this is how VNIR tells the bulk silicate mineralogy. So that's, again, what I'm going to be focusing on. Other important features are the Radiometer bands that I've labeled here in green, and the transparency features that I've labeled in blue, and these all tell us about the structure and chemistry of our material. So when we combine that and we look at the lunar environment's effect on our spectra, we get some big changes in the data set. So in black, we have a spectrum that's been measured on Earth, and then in blue, we have the same Forsterite that's been measured under simulated lunar environment conditions. And you can see this CF feature that we're using to identify our mineralogy has shifted quite a bit. The Radiometer bands and the transparency features haven't really changed in their position, but the spectral contrast is much different. So all of these factors we need to take into account when we're looking at an airless body, not just the moon, but asteroids as well. So for my project has focused on two parts. The first is a collaboration with Young et al. They put out a paper last year. They did laser pulse radiation experiments to simulate space weathering on some more olivine grains, and I have them, some of their images shown here. Hopefully you can see visibly the material gets darker as we increase the radiation, and we also form these, the nanophase iron in the rims of the grains. And notably, for the visible and near-infrared reflectance spectra, as we increase our irradiation, so that's going down this way, we're losing the features, we're getting that red slope in our spectra, and they're all getting darker. So then for my experiments that I did, I just darkened some olivine using nanophase carbon. And this is certainly not on the same scale. We have much larger carbon particles. Here's a nice TEM image of them, and it's about 94 nanometer size for all of our carbon. And the goal was to try to get rid of some of the same effects you get from the nanophase iron, and really focus on the albedo effects and how that's changing our mid-infrared spectra. So what we did was I measured the albedo using ASD field spectrometer, looking at specifically at the 750 nanometer wavelength to measure albedo. And then we have, at Stony Brook, we have Parsec, which is this nice little box here, in which we can put all of our soil samples and simulate those lunar conditions on the surface. So we can vacuum it out, get to about 10 to the minus 6 millibar, and make it cold, and then heat it both from above and below so that we can try to set up that same thermal gradient that we know exists on the moon. So for the results, these are the visible and near-infrared reflectance spectra for both sets of samples. On the left, we have the irradiated samples, and then on the right are just my carbon-darkened samples. So again, in reflectance, you can see that as we get to the more space-weathered samples, we lose the large features, and they're overall getting darker, so they're reflecting less. But what's notable, again, is that my samples don't have the same red slope that we see in the radiated samples. So again, trying to separate those two effects. Okay, so now the important part, the mid-infrared. Again, we have the irradiated samples on the left and my carbon samples on the right. And what I'm really looking at is that we see the CF shifting in both sample sets, and it's shifting farther to the right. So that tells us that hopefully this is more of a albedo effect than the overall space weathering process effects on the regolith. We also see that the Reststrahlen band, I've just highlighted one of them, is not changing position, but the contrast does change in a semi-predictable way in these samples. So now to reiterate the effects of albedo, I've plotted up all of the samples. I have in blue and green are both of my samples at two different size fractions, and I've plotted out the CF position versus the reflectance at 750 nanometers. And then in red are the irradiated samples, and this gray bar represents the CF position if we measured it on Earth. So you can see that these are all kind of far off of that Earth-measured CF position, but they do trend linearly with albedo. So hopefully we can use this to maybe calibrate our data analysis. And then, so this is all done in the lab, right? So we have very high resolution data. So what I want to do was downsample these to diviner resolution to see if we can still see the same changes. So these are the same, again, irradiated on the left and the darkened on the right of all of our samples at diviner resolution, this 3-point spectrum. And we can see the changes still, which is great. So hopefully we can use this to help, again, calibrate future data sets or contribute to the current analysis for diviner. And let's see, so then just to leave you with some of the conclusions, we have a linear trend between albedo and CF position, and these effects are detectable at even low diviner resolution. So hopefully when we're looking at other airless bodies, such as the asteroids that have missions going to them, we can use the same type of technique to calibrate our spectral library so that we can better analyze the remotely sensed data sets. And hopefully I'm going to be looking at some other minerals as well, and some mixtures and soil samples to really help flesh this out. So thank you, and I'll take any questions.
Does this mean that this kind of negates the Glotch's paper about lunar swirls and what they were seeing in the diviner data? Because I mean, maybe it's not really due to differential weathering, but it is due to only albedo.
Well, I think that is kind of a different beast in the magnetic properties like we just saw in MIHAIS as well, and how that has changed. That seems to be changing the orientation effects. I can't remember. One of the students at Loon GradCon actually was talking about this as well. So hopefully, if you're here, you can refer to him about that. So I don't think it's quite the same effect, but it's something that can help us interpret the composition, knowing that as well.
I had kind of a technical question about the experiment.
Mm-hmm.
When you zap it with the laser and then look at it with the spectrometer, how big an area are you looking at? And sort of related to that is how much coverage do you have with the laser spots? And does that possibly affect the overall result?
Unfortunately, I didn't do the laser part of the experiment, so I can't quite speak to the spot size that they had. I can refer you again to their 2016 paper. But as far as what we are measuring in the spectrometer, our samples are about 2.5 centimeter diameter cups filled with soil. So it's probably a bit less than that is what's convolved for our actual spectra. Okay.
All right.
All right.
Thank you very much.
Thank you.